Module 2, Lecture A, Conditional Checks. By the end of this lecture, you will be able to write Boolean expressions that compare calculated values with engineering limits, use if, elif, and else statements to classify civil engineering conditions, and create clear warning messages for results that exceed specified criteria. Boolean logic. Compare limits. In engineering, Boolean logic helps turn calculation results into clear decisions by checking them against required limits. Values such as stress, deflection, or pavement thickness must be compared with performance or safety criteria to determine whether they pass or fail. This means calculations are not enough on their own. They must be interpreted through true or false checks that support sound engineering decisions. When evaluating limits in engineering, first identify whether the value is a maximum or a minimum. A result above a maximum, such as crack width or pipe pressure, indicates a problem, while a result below a minimum, such as concrete strength or sight distance, means performance is inadequate. The same number can be acceptable or unacceptable, depending on whether the limit is a ceiling or a floor. When comparing calculated results with limits, use exact wording and make sure the units match. Engineers should also define whether a value equal to the limit passes or fails, since that affects the safety margin. These comparisons turn engineering requirements into clear true or false decisions that make analysis consistent and defensible. Python code. Compare limits. Compare calculated values against engineering limits to support safe decisions. Simple true or false results indicate whether limits are met, while clear messages make the review easier and safer. Two calculated engineering values are defined for later performance checks. Structural deflection is 18.5 millimeters, and settlement is 27 millimeters. These measurements will be compared with preset limits to evaluate the structure's performance. The maximum allowable deflection is set at 20 millimeters, and the maximum allowable settlement is set at 25 millimeters. These limits define how much a structure may bend or sink before safety and integrity become a concern. We verify safety by comparing the calculated deflection and settlement against their allowable limits. Each comparison gives a true or false result, showing whether the value is acceptable. These checks indicate whether the engineering values stay within safe limits and support the next decision. The code checks whether the deflection and settlement values meet their allowed limits. It prints a true or false result for each one, giving a quick confirmation of whether both engineering criteria are satisfied. The beam's serviceability is classified by checking whether deflection and settlement stay within their allowable limits. If both are acceptable, the beam passes the serviceability check. If one or both exceed limits, a warning identifies the issue. This provides a clear basis for engineering judgment. The code displays the engineering decision message, summarizing whether deflection and settlement meet serviceability limits. This gives a quick, clear result of the structural assessment for decision-making. Deflection and settlement margins show how much capacity remains before reaching allowable limits. Each margin is found by subtracting the calculated value from the maximum allowed value, giving the remaining amount in millimeters. These margins indicate how close the structure is to its serviceability limits. The code reports the remaining safety margin for deflection and settlement in millimeters. Each margin is found by subtracting the actual value from the maximum allowable value. These results show how much capacity remains before the engineering limits are reached. The script checks structural serviceability by comparing measured deflection and settlement with their allowed limits. The deflection of 18.5 millimeters is acceptable because it is below the 20 millimeter limit, while the settlement of 27 millimeters exceeds the 25 millimeter limit. It reports these checks as true or false, classifies the beam condition with an appropriate warning, and shows the remaining margin for each value. Engineering limit checks. Engineering limit checks use Boolean logic to turn calculations into clear, true or false decisions. In civil engineering, this means checking whether a computed result, such as beam deflection, stays within an allowable limit. The focus is on whether the design criterion is met, so programs and automated systems can evaluate the decision consistently. Engineering limit checks must clearly state whether a value is being tested against a maximum, a minimum, or an acceptable range. Maximum limits flag values that are too high, while minimum limits flag values that are too low. And some checks require staying within a defined band. Using Boolean logic makes these conditions precise, reducing ambiguity when reviewing results or comparing design options. Engineering limit checks must clearly define whether limits are inclusive, what units are used, how tolerance is handled, and when equality is acceptable. A value equal to a limit may pass in some standards, but require a safety buffer in others. Using consistent units and clear Boolean decisions ensures numerical results are judged correctly for safety and compliance. Python code. Engineering limit checks. Boolean checks turn engineering results into clear, true or false decisions by comparing them with defined limits. Clear failure messages help reviewers quickly understand what went wrong. The actual deflection is recorded as 0.82 inches, while the allowable limit is 0.75 inches. These two values will be compared to determine whether the deflection meets the accepted engineering limit. Check whether the actual deflection is within the allowable limit by comparing it with the maximum permitted deflection. If the actual value is less than or equal to the limit, the deflection is acceptable. The result of this check is then printed as a confirmation. The bearing's current pressure is set at 185 kilopascals, while its allowable capacity is 200 kilopascals. Comparing these values shows whether the actual pressure stays within the safe operating limit. This check compares the current bearing pressure with the allowable capacity. If the pressure is less than or equal to the limit, the check passes. The result is then reported to show whether the bearing pressure is within the allowable range. The factor of safety is set to 1.45, while the minimum required value is 1.5. Since the actual value must meet or exceed this threshold, this result is slightly below the acceptable limit. Check whether the factor of safety meets the minimum required value. If it is greater than or equal to the minimum, the safety condition is acceptable. The result of this comparison is then displayed to confirm whether the requirement is met. The code classifies engineering check results using conditional logic. If deflection, bearing pressure, and factor of safety are all within limits, it reports that all checks pass. If the factor of safety is too low, it gives a specific warning. Otherwise, it warns that a serviceability limit has been exceeded. The code prints a final status message that summarizes the engineering checks. It reports whether all checks passed or highlights warnings about the factor of safety or serviceability limits. This gives a clear, concise conclusion based on the earlier Boolean results. This script checks key engineering limits by comparing calculated deflection, bearing pressure, and factor of safety against their allowed values. It prints whether each check passes or fails, then gives an overall status. If all checks pass, it reports success. If the safety factor is too low, it warns about the safety margin. Otherwise, it notes that a serviceability limit has been exceeded. Threshold checks. Threshold checks let engineers make clear yes or no decisions by comparing results with required limits. In civil engineering, values like beam deflection or stormwater flow matter only when judged against standards such as serviceability or capacity. Boolean logic makes this comparison precise, reducing ambiguity and supporting clear engineering decisions. When writing a threshold check, make sure the comparison matches what is physically concerning. Some engineering values are unsafe when they are too high, others when they are too low, and some must stay within an acceptable range. A good Boolean expression reflects that context, so the result correctly identifies a problem. Effective threshold checks depend on using consistent units, assumptions, and tolerances. A comparison is reliable only when the calculated value and the limit refer to the same context, such as the same measurement units and time scale. Engineers also need to separate strict regulatory limits from design criteria that allow judgment and safety margins. Done well, these checks make calculations clearer and help connect analysis to practical engineering decisions. Python code. Threshold checks. Threshold checks compare a result with a set limit and produce a true or false outcome through a Boolean expression. Civil engineers use these checks to support clear decision-making. We store the calculated beam deflection in millimeters so it can be used later. This value shows how much the beam bends under load and helps determine whether it stays within structural limits. We store the beam's allowable serviceability deflection limit in millimeters. This limit defines the maximum acceptable deflection under normal use, so actual measurements can be checked against it to confirm the beam performs within acceptable bounds. This check compares the beam's calculated deflection with the allowable limit to decide whether it meets engineering standards. The result is true when the deflection is within the limit, and false when it exceeds it. The calculated culvert flow is 125 cubic feet per second. This actual flow rate can be compared with the culvert's design capacity to determine whether the flow is within acceptable limits. The culvert's design capacity is set to 110 cubic feet per second, which represents the maximum flow it is built to handle. This value is later compared with actual flow to check whether the culvert is operating within its design limits. This check compares the calculated flow rate with the culvert's design capacity. If the flow is greater than the capacity, it records that the capacity is exceeded, signaling a possible problem with the culvert handling the flow. The calculated factor of safety is 1.42. This indicates how much stronger the structure is than the minimum required strength, helping confirm its reliability and safe performance. We set the minimum acceptable factor of safety to 1.5. Any value below this threshold is considered inadequate, helping ensure the design meets required safety standards. This check compares the current factor of safety with the required minimum. If it is lower than the minimum, the result is true, signaling a possible safety concern. The code prints a quick status summary for key engineering checks. It reports whether beam deflection is acceptable, whether culvert flow exceeds design capacity, and whether the factor of safety falls below the required minimum. These outputs help engineers quickly identify possible overflow or safety concerns. The checks compare key engineering values against their limits, beam deflection, culvert flow capacity, and minimum factor of safety. If any value fails its threshold, a specific warning is printed. If all checks pass, the system reports that the engineering thresholds are acceptable. This script shows how Boolean comparisons can support engineering decisions by checking calculated values against design limits. It finds that the beam deflection is acceptable, the culvert flow exceeds capacity, and the factor of safety is too low. Because the culvert flow is the first failed condition, the script prints a warning about that capacity problem. Branching rules. If statements. An if statement lets a program make decisions by running certain actions only when a condition is true. In civil engineering, this is useful for checks, such as whether pavement roughness needs maintenance or whether a slope safety factor is too low. In this way, if statements help programs respond to design limits and safety criteria. In civil engineering programs, an if statement should directly reflect the engineering decision being made. It turns standards and professional judgment into consistent checks, such as flagging high water levels, low concrete strength, or excessive foundation settlement. This helps the program make repeatable decisions that match the intended engineering criteria. Clear if statements help engineers apply decisions consistently across complex projects. A precise condition prevents ambiguity, and the resulting action should match the seriousness of the situation, such as flagging unsafe readings or tests that need review. Used carefully, these simple decisions can automate routine classifications while preserving the logic of engineering criteria. Python code, if statements. Use if statements to perform simple engineering checks by comparing calculated values against clear limits. Then print short classifications so learners can quickly understand whether each result meets the required condition. A measured settlement value is stored in millimeters to help assess structural integrity. In this case, the settlement is 32 millimeters, representing the observed movement in the engineering context. A settlement limit is set to 25 millimeters, representing the maximum acceptable structural settlement for serviceability. Actual settlement measurements can then be compared with this limit to decide whether further action is needed. The settlement is checked against the serviceability limit to see whether it is acceptable. If it is greater than the limit, a warning status is set to indicate that the serviceability threshold has been exceeded. The program displays the measured settlement in millimeters, then reports whether it exceeds the serviceability limit. This status message comes from the earlier condition check and warns the user when the settlement is too high. The script stores the channel's water level as 2.4 meters. This value can then be compared with an alert threshold to help monitor whether the water level stays within safe limits. An alert threshold for water level is set at 2 meters. This limit can be compared with actual channel measurements to decide whether the water level needs attention. The process checks whether the current water level is above the alert level. If it is, it creates a warning message that the channel water level needs review. This simple comparison helps flag possible water level issues for attention. The code displays the current water level in meters, then reports its status. If the level is above the alert threshold, it prints a warning that the channel needs review, helping prompt timely action. The script uses simple condition checks to flag two engineering concerns. It compares settlement with a serviceability limit and water level with an alert threshold, then prints each value with a warning only when the limit is exceeded. This gives quick feedback on whether the parameters need review. Else conditions. An else condition provides a final outcome when earlier conditions are not met. In civil engineering decisions, it helps ensure no case is left unresolved, such as classifying pavement with no severe or moderate distress as acceptable or low priority. Because it covers all remaining possibilities, it does not need a separate test, and it makes the decision process clearer and more complete. The else condition depends on the order of the conditions before it, because it runs only when all earlier branches are skipped. This makes careful sequencing important for correct classification. For example, if unsafe and monitoring cases are checked first in a slope stability review, the else branch can cover acceptable cases, but poor ordering can incorrectly label borderline cases as satisfactory. An else condition can make a classification system complete by giving normal values a default outcome, but it should not hide invalid, missing, or unusual data. Check those cases before the final else branch, so the default result represents a real category and does not mask data quality problems. Python code, else conditions. Else branches finish the classification process by handling the remaining cases after earlier checks have addressed the risky ones. Anything not matched before reaches the final else branch. We define a list of slope names to label the slopes being analyzed: north cut, east fill, and west bench. These labels will help identify each slope during the safety assessment. The code stores the calculated safety factors for multiple slopes in a list. These values are then used to check each slope against the safety criteria and classify its condition. A loop is used to classify each slope condition by pairing each slope name with its safety factor. The zip function combines these two lists, so each slope can be evaluated one at a time. This prepares the data for the conditional checks that determine each slope's safety status. The code flags a slope as unsafe when its safety factor is less than 1. In that most critical case, it sets the status to require immediate engineering review, ensuring urgent risks are identified first. When the safety factor is below 1.3, the slope is marked for monitoring. This means it is not considered immediately dangerous, but it should receive extra inspections after rainfall to catch possible problems early. The else statement handles any cases not matched by earlier conditions. In this example, it marks the safety factor as acceptable, meaning it meets the required criterion. This keeps the logic simple by treating anything not unsafe or needing monitoring as acceptable. The code summarizes each slope's safety assessment by reporting its name, factor of safety, and classification status. This gives a quick overview of the slope's condition and any needed action. The code explains that the else branch handles any cases not covered by the earlier if or else if checks. In this way, else works as a catch-all, helping ensure the classification logic accounts for all remaining possibilities. The script checks 3 slopes by comparing each factor of safety to set limits. A value below 1 marks a slope as unsafe and needing immediate review, while a value from 1 to 1.3 calls for monitoring and inspections after rainfall. Higher values are treated as acceptable. This shows how an else condition can catch all remaining cases and give each slope a clear safety status. Else conditions. The else condition is the final fallback in a decision process, used when none of the earlier checks apply. In civil engineering, it helps ensure every condition is classified against set thresholds, such as marking pavement as acceptable when no distress category fits. This makes the logic complete, clear, and reliable. The else condition should be treated as a catch-all not another test. It runs only after more serious checks, such as instability or excessive deflection, have failed. This order lets engineers flag urgent problems first and use the else branch for normal or low-risk cases, making results clearer and reducing misclassification. Using an else condition makes warning systems and engineering reports clearer by ensuring every outcome is deliberately classified. If no problem is detected, such as an undersized culvert or failed material test, the else condition marks the result as adequate or passing. This helps users trust that satisfactory results were checked intentionally, not simply overlooked. Python code, else conditions. Else branches finish the engineering classification by covering the cases left after earlier checks handle the most severe conditions. Anything remaining falls into the safe branch. 2 pavement distress measures are set for later condition classification. Cracking covers 7.5% of the surface, and rut depth is 0.18 inches. These values will be compared with predefined thresholds to assess pavement condition. The pavement condition is classified by checking cracking percentage and rut depth against set thresholds. Severe distress is flagged when cracking is above 25% or rut depth exceeds 0.75 inches, leading to a rehabilitation recommendation. Lower thresholds identify moderate distress, which calls for maintenance soon, and minor distress, which calls for routine monitoring. If none of these limits are exceeded, the pavement is considered acceptable with no warning needed. The code displays the cracking percentage and rut depth in inches, which are key measures of pavement distress. These values show the extent of visible damage and provide the basis for classifying the pavement's overall condition. The code displays the final pavement condition classification. It reports the severity determined by earlier checks, helping users understand the result of the pavement measurement analysis. The script classifies pavement condition using cracking percentage and rut depth. High cracking or deep ruts are marked as severe and call for rehabilitation, while lower but noticeable distress is labeled moderate or minor, with maintenance or monitoring recommended. If the measurements do not meet these thresholds, the pavement is considered acceptable. The output reports the measurements and the recommended condition category. Engineering warning criteria. Threshold warning messages. Threshold warnings in engineering signal that a result has passed an acceptable limit, but is not yet critical. They turn technical measurements into clear guidance, such as recommending monitoring, maintenance, or review. Their purpose is to show that a boundary has been crossed and that specific attention is needed before conditions worsen. A good threshold warning should give enough context for the reader to understand the problem immediately. It should name the monitored condition, state that the threshold has been exceeded, and explain the engineering meaning in clear professional language. For example, it may connect excessive stormwater flow depth to overtopping risk, or an out-of-range concrete slump to possible mix issues. Avoid vague wording and make the consequence of the breach clear. Threshold warnings should match the seriousness of the situation. If every alert sounds urgent, engineers may become desensitized or react too strongly. Effective warnings draw attention while guiding appropriate next steps, such as checking data, planning maintenance, or continuing observation. Matching tone to risk supports clearer communication and better decisions. Python code. Threshold warning messages. Threshold warnings help turn numerical limits into clear decisions. In this civil engineering example, The messages identify when limits are reached while staying firm, neutral, and not overly critical. A list of checks stores engineering measurements to monitor. Each entry includes the measurement name, its measured value, the allowed threshold, and the unit. This structure makes it easy to compare each value with its limit and decide whether action is needed. We start by creating an empty list to hold short status messages. This gives us a simple place to collect the results of threshold checks, so they can be organized and printed later. The code reviews a set of engineering measurements by checking each measured value against its allowed limit. For each item, it creates either a warning if the value is too high or a confirmation if it is within the acceptable range. Each resulting message is stored for later use. The code stores each new status message in a shared list, keeping both warnings and successful check results together. This makes it possible to review and summarize all engineering check outcomes later. The code goes through each status message and displays its content in the console. This ensures the user sees immediate feedback for every engineering check, including warnings and confirmations that conditions are within limits. The code counts how many messages need attention by checking which ones begin with the word warning. It treats each matching message as one and adds them together to get the total number of warnings. The code prints a brief summary showing how many checks need attention out of the total checked. It compares the number of warnings with the overall number of checks, giving management a quick view of how many issues may require follow-up. The script checks engineering measurements against safe thresholds and reports their status. For each measurement, it compares the recorded value with its limit, warning when the value is too high and confirming when it is within range. It then prints all results and summarizes how many checks need attention. Threshold warning messages. Threshold warnings in civil engineering show when a calculated result has passed a set limit, but does not yet indicate an emergency. They turn numerical checks into clear guidance for timely decisions. For example, a beam deflection warning should explain that the issue concerns serviceability, such as performance and comfort, rather than immediate danger. Good warnings state the condition, why it matters, and what level of attention is needed. Threshold warning messages should be clear, concise, and tied directly to the engineering criterion being checked. Instead of vague wording, state exactly which condition exceeded its limit and what action may be needed, such as reviewing storage capacity or inspecting excessive movement. This helps teams with different roles understand the issue quickly, reduce ambiguity, and decide whether to revise the design, collect more data, or escalate the concern. Threshold warning messages must be serious enough to get attention without causing unnecessary alarm. In engineering, they often show that a system is moving away from acceptable conditions, such as excessive wall movement or low concrete strength. A good warning connects calculations to real conditions, supports sound judgment, and helps prompt timely action before small problems grow. Python code, threshold warning messages. Threshold messages turn calculation results into practical engineering decisions. They use limits to classify outcomes without overstating risk, and effective warnings clearly state the condition, the criterion, and the required response. The beam span is 240 inches, and its measured deflection under load is 0.92 inches. To check whether this is acceptable, the allowable deflection is found by dividing the span by 360, giving the maximum safe deflection limit. The code compares actual deflection with the allowable limit to find how much it exceeds the limit. It then sets a default status of review needed, and prepares an empty warning message to be filled in later based on the deflection results. The logic classifies beam deflection by comparing actual deflection with the allowable limit. If it is within the limit, the status is acceptable. If it is only slightly over, up to a quarter inch, it gives a threshold warning and recommends reviewing performance and comfort. Larger exceedances receive a high warning and call for senior engineering review. The code prints a short engineering warning summary for a beam deflection check. It reports the beam span, the allowable deflection calculated as the span divided by 360, and the actual measured deflection. Both deflection values are shown to 2 decimal places, making it easy to compare the measured result against the limit. The output reports the deflection status, indicating whether it is acceptable or needs a warning. It then gives a warning message with the key implications and any required response. Finally, it advises documenting the result and planning follow-up so the engineering team can act appropriately. This script checks whether a beam's measured deflection stays within an allowable limit, calculated as the span divided by 360. It classifies the result as acceptable, a threshold warning, or a high warning, depending on how far the deflection exceeds the limit. The output reports the span, allowable and measured deflections, the classification, and the recommended follow-up, such as performance review or senior engineering review. Critical warning messages. Critical warning messages signal unsafe conditions or serious limits being exceeded, so they require immediate engineering attention. In civil engineering, they may indicate issues such as overstressed beams, unstable slopes, or floodwaters reaching a roadway. Their purpose is to clearly communicate urgency and prompt rapid review or intervention. A critical warning message should state exactly what failed, which limit was exceeded, and why the result matters. Avoid vague wording and give enough specific context for engineers or operators to understand the issue even without the full data. Clear automated warnings support faster, better-informed responses. Critical warning messages should be professional, direct, and specific, without sounding unnecessarily alarming. They should clearly state the engineering issue, its implication, and the needed response, such as reviewing assumptions, stopping work, inspecting components, or consulting an engineer. For example, excessive floor deflection should prompt an engineering review, while exceeded storm drain capacity should identify a serious flooding risk. Clear, concise warnings support faster and safer decisions. Python code, critical warning messages. This example creates critical engineering warning messages by checking results against serious limits and clearly stating which engineering criterion has been exceeded. The beam stress is 285 megapascals, while the allowable stress is 250 megapascals. Comparing these values shows whether the beam stays within its safe engineering limit. The slope's current stability is represented by a slope factor of 1.05, while the required safety threshold is a minimum factor of 1.3. These values are used to judge whether the slope meets acceptable stability standards. The code stores 2 key flood-related heights, the floodwater level and the road's protection level, both measured in feet. These values are later compared to determine whether floodwaters rise above the road's protection and indicate a possible flood risk. The code compares beam stress with the allowable stress and assigns a status message. If the stress is above the limit, it flags a critical warning and recommends engineering review. If it exactly meets the limit, it advises careful verification. If it is below the limit, it confirms the beam stress is acceptable. The code compares the slope stability factor with the required minimum safety margin. If the factor is below the minimum, it reports a critical stability issue. If it matches the minimum exactly, it notes that the requirement is just met. If the factor is higher than the minimum, it indicates there is no immediate concern. The logic compares the flood level with the road protection level to choose the appropriate warning message. If the floodwater is higher, it signals a critical condition and suggests reviewing a possible road closure. If the levels are equal, it notes that the water has reached the protection limit. If the floodwater is lower, it reports that the situation is okay. The code presents a concise set of engineering warning results. It first introduces the warning criteria, then displays the outcomes for beam stress, slope stability, and flood elevation. Together, these messages show whether each condition is acceptable, exceeded, or needs further review. The script compares engineering calculations with safety limits for beam stress, slope stability, and flood level. In all three cases, the results are critical. The beam stress is too high, the slope stability margin is too low, and the flood level exceeds roadway protection. Each warning points to needed action, such as engineering review or possible road closure. In this lecture, you learn to write Boolean expressions that compare calculated values with engineering limits. Use if, elif, and else statements to classify civil engineering conditions. And create clear warning messages for results that exceed specified criteria. In the next lecture, Lecture B, we will go over loops and iteration.
Thank you for your attention. See you all in the next lecture.